In Lesson 5.6, Differential Equations, Growth and Decay, we'll take a look at a class of differential functions in which the rate of change of some variable is in some way proportional to that variable itself. See, what we've been doing all this time is saying that the rate of change of y is proportional to x in some way or another. But in this lesson, we're going to explore where the rate of change of y is proportional to y. It's an interesting situation, and it's one that, with enough practice, we'll be able to deal with easily, but we do need to get there with that practice. So that's the purpose of this lesson. The crescendo of this lesson, the climax if you will, is when we make the connection between these differential equations and the idea of half-life, which is something that you should have knowledge of from previous math or even science courses. We'll deal specifically with the half-life of the carbon-14 isotope, which is used a lot in radiometric dating. So we'll take a look at a couple examples dealing with that. But before we get to anything too major, let's go ahead and begin with a simple differential equation here in example A. So here we go, right off the bat in example A, we're dealing with a differential equation that involves both y and y prime. Now we're asked to solve for y, and when it means solve for y, it means we need to get y in terms of x only. So it does no good to have this y prime hanging around. We'll need to handle that situation. But before we do, and before we get too far into this problem, I do want to remind you of a very important fact about exponents that you perhaps learned in Algebra 1 or Algebra 2, and that's simply if you have a base to an exponent of the form m plus n, that we can actually split that up into a to the m multiplied by a to the n. This is a very important fact, and I am going to reference this later. By the end of this lesson, it'll be common sense why I'm telling you that now, but we'll get to that in a moment. Anyway, back to this problem. Let's go ahead and solve for our y prime. After all, if we want to integrate, it's y prime that we kind of have to get by itself. On the right side, we'll have 100x minus xy. Now, this y hanging out over here is not going to do us any good, so we need to somehow get that y over to the left side. And the way we're going to do that, well, we can actually factor the right side. Take a look that there's x's in both of these terms. So if I factor it out, this is actually what I'm going to get. As far as the left side, this y prime, remember that y prime is kind of the same thing as saying dy dx. Because in my next step, I'm going to take this 100 minus y factor and move it to the left. And I'm going to take this dx term and move it over to the right. Watch how beautiful this is going to be. This is what it's going to look like. I'll have dy over 100 minus y. And then on the right side, I'll have x dx. Notice how I did that. Hopefully that makes a lot of sense because we'll be doing a lot of this lesson. So, at this stage, I can go ahead and integrate both sides. And you might want to pause here for a second and say, but wait a minute, how are we going to integrate the left side? And if that's the case, I'll simply remind you that the top is a derivative of the bottom. And when the top is a derivative of the bottom, that should bring to mind the natural logarithm. However, we need to be very careful here. The top is not exactly the derivative of the bottom because what is the derivative of 100 minus y? In other words, the derivative with respect to x of 100 minus y is actually going to be negative y prime. And we do not have that here. So what we're going to have to do is introduce a negative on top, balance it with a negative outside, and now we can go ahead and integrate. This will be negative natural log, the absolute value of 100 minus y. On the right side, we'll simply have x squared over 2. Don't forget your plus c. These plus c's are extremely, extremely important when dealing with differential equations. So always remember your plus c. Before we proceed, we actually need to get rid of this negative now because I want to get rid of the natural log. Can't really do that while the negative is here. So if I multiply both sides of this equation by negative 1, I'll get that. And you might question this. Shouldn't the plus c turn into a minus c? You can do that if you like. But because c is any constant, it really doesn't matter if it's plus c or minus c. The value of the constant will override the sign either way. So it's all good. Alright, so if I want to get rid of the natural log now, I'll go ahead and exponentiate both sides. What that means is on the left, I'll have 100 minus y. On the right side, I'm going to do something very tricky here. Notice that this is e to the power of something plus something. Now I'm going to refer you back to where we started. Using that rule, what we can actually say is this is e to the c power multiplied by e to the negative x squared over 2 power. And, well, let me present this fact to you. Whatever the value of c is, e to the c is a constant. Whatever c is, this will be a constant. So I can actually rewrite this as some arbitrary constant, e to the negative x squared over 2. Now, be aware, be very careful here. This c and this c are not the same values. Nevertheless, they're both constants, so it's all good. And in fact, it looks like I really only have one step left here. I'm almost done with this problem. If I bring this up here, if I want to solve for y, looks like what I'm going to end up with is just 100 minus c e to the negative x squared over 2. There it is. There is y. Go ahead and differentiate y, see what you get, and then plug it back into our original formula. Plug y itself back into the original formula and see if it doesn't all equal 100x when you simplify it. I bet it does. So those are differential equations. They are a process. You do need to go through all the steps. A lot of times we will end up with a natural log, so we will end up with an e. And just remember this little trick right here, because this is going to happen over and over and over again. In fact, I'll prove that to you. Let's go ahead and try example B. So in example B, we're going to do much the same thing we did in example A. We're given this differential equation, which quite honestly is a quite bit easier than the one in example A, but regardless of that, we'll solve this and find the general solution for this differential equation. That'll be a function y, which is in terms of t. However, this time around, we're not just going to stop at the general solution. We're going to use this point 0, 10 to find our particular solution. This point 0, 10 is actually referred to as an initial value. And the reason we refer to it as an initial value is because this point occurs when time equals 0, time being the x variable. So when time is 0, of course, that's why we call it initial. And with that, let's go ahead and take a look at this problem. Well, I had noticed that I have a dy and a y, and I should work to get those on the same side. And then I should work to get everything else on the other side. So how can we do this here? It's actually not going to be too difficult. I'm simply going to multiply both sides by dt and divide both sides by y. And so when I multiply both sides by dt, my right will look like this. When I divide both sides by y, my left will look like this. And now I'm good to go ahead and integrate, much like I did in example A. So doing this, of course, on the left, we've already been refreshed on the fact that that's the natural log of the absolute value of y. And then on the right, the integral of 3/4 dt is simply going to be 3/4 t plus our constant of integration. Don't forget that. Alright, well, we need to get y by itself, so if we exponentiate both sides, we'll simply get y equals, remember that trick from example A? Remember that trick where we pulled the c down and turned it into some other constant? Well, here we go again. ce to the 3/4 t power. Alright, so that is our general solution to this differential equation. That's our general solution, but if we want our particular solution using our initial value 0, 10, all we need to do is just substitute some points in. 10 will go in for y, of course, and t will turn into the 0. But what will be the exponent then? 3/4 times 0? Well, that's just 0. So hopefully you can do a little mental math here yourself and find out that c is going to have to equal 10, meaning that our particular solution for this differential equation is going to be y equals 10 e to the 3/4 t. And there it is. You can verify for yourself that this does in fact go through the point 0, 10. And if you differentiate this, you can also verify for yourself that the derivative of y with respect to t actually is 3/4 times this function y. So pretty cool. Go ahead and try it yourself. See that it works. And with that, we'll move on to one of our best old friends, the slope field. Of course, every slope field problem we've done to this point has involved a differential equation, even though we really haven't explained why. But hopefully now with example C, it'll all mesh together in a very beautiful, fun, and exciting way. Here we go with example C. So example C looks to involve what seems to be a particularly easy differential equation. It simply says dy dx equals x times y. Doesn't really seem like it would get too much easier than that, and to be perfectly honest with you, it's not that difficult of a problem. This differential equation would produce this slope field that you see here, and it is quite interesting to note that above the x-axis there seems to be graphs that go up without bound, while below the x-axis it seems that the graph would decrease without bound. And that is in fact the case, because as I'm going to show you right here, there is what happens if we have a graph north of the x-axis and if we have a graph south of the x-axis. Of course, the graph on top does go through that blue point 0, 0.5, and that's the particular solution that I'm looking for. So let's go ahead and solve this out. Once again, I'm going to try to get all the y's on one side of the equation and all the x's on the other side. So I simply did that by dividing by the y and multiplying by the dx. No big deal. But if we go ahead and integrate at this point, now we can see how this would result in the natural log of y equals, well, once again, x squared over 2 plus your constant of integration. So if we go ahead and exponentiate, this is starting to get old, but it is necessary. We'll end up with c e to the x squared over 2. And there is our general solution. Now, for our initial value, we do want it to go through 0, 0.5. So let's go ahead and plug in some values. Y will become 0.5. C, we're not sure. That's what we're solving for. And then we'll have e to the x squared over 2. But notice, x is 0. So that's pretty handy. It appears that c is simply going to be 1/2, or 0.5 if you like. It's interesting to note here that when dealing with these equations, it's not the plus c that we can change and make the thing go up or down. It actually becomes a multiplier that we have to vary. So our particular solution for this differential equation will be y equals 0.5 e to the x squared over 2. You can graph that on your calculator and see that it does in fact give us this graph up here north of the x-axis. However, if you are graphing this on your calculator, just to see some other solutions, change the 0.5. Don't add or subtract values, change the c. And c here is a scalar multiplier. Change the 0.5 and see that you'll get other solutions like this one down here. So there you go, another example of differential equations. Example D is going to be very interesting because it doesn't come out and give us the differential. Nevertheless, it will be one step in the process of getting to the exponential growth and decay model, which we will also get to very soon. In example D, I'm given a rate of change proportion problem. These are kind of similar to the problems that are given in Algebra 2 when you first learned about direct and inverse proportionality, but this time we're dealing with the rate of change being proportional. So let's see what this looks like. When we say the rate of change of p, of course we're talking about dp dt, and if that's proportional to p, then it's not going to necessarily equal p, but it's going to equal some version of p. So I'll put my k here. This is what we refer to as the proportionality constant that keeps things from being equal, but rather just proportional to. Alright, well, we're given some other information, but before we get to that, let's go ahead and solve this differential equation that we have right here. Similar to our last few examples, we're going to get the p things on one side, and we'll get everything else on the other side. So that we'll have an equation that looks kind of like this. And this, of course, we know how to integrate. This would give us the natural log of the absolute value of p, and over on the right side we'll simply have kt plus c. And of course there is that one last step. We need to exponentiate both sides, and when we do that, we're going to end up with our general equation to this, or general solution to this rather, P equals CE to the KT power. Now, I want you to keep an eye on this because this is going to pop up again over and over and over throughout these notes and throughout this assignment. So I'm boxing it in because I am going to refer back to this later. Anyhow, now that we know our general solution to this, let's see what happens with our initial condition. The initial condition, of course, is 0, 5,000. And if I go ahead and make some substitutions, let's see, I'll have 5,000 equals C e to the k multiplied by t, which is just 0. Oh, well, that means we have e to the 0, and that tells us what c must be. C has to be 5,000 then. And what that tells me then is I have a particular solution here, kind of, which is going to be P equals 5,000 e to the kt power. Unfortunately, I still have this k, this proportionality constant, and I can't just go on through life not knowing what k is. So now let me use the other point that I'm given. This is going to be the point 1, 4,750. And if I plug in some values here, what I'll get, 4,750 equals 5,000 e to the k times 1 power. See, now that I've taken care of t, I can go through and solve for k. So let's go ahead and do that. I'm going to work this out, but hopefully you can do it on your own. If I divide both sides by 5,000, I'll simply get 0.95 equals e to the k. And of course, to get rid of the e, all I really need to do is just natural log both sides. So, having natural log both sides, what we should get is that k is around, let's see here, I get around negative 0.051. And what does that tell us? Well, we can go ahead and finish this part by saying we know for certain now that P is 5,000 e to the k t. So I'm writing this real big and obnoxiously in the middle here because that is the equation that we come up with. P, or rather the rate of change of P, is proportional to P. That's the solution to a differential equation right here. We see that at time equals 0, if we plug 0 in for t, we do get 5,000, so our initial value holds. And if you plug 1 in for t and work all this out, you will get 4,750. All we have left to do here is to solve the last part of this problem, which simply asks, what is the value of p when t is 5? So, let's see, if I call this p of t, what I can do is go ahead and just put 5 in for t. And if I just work all this out, I'm not going to go through the steps of it because, quite honestly, I just did all this in my calculator. But what I got was 3,868.904 for P. Does this make sense? Well, we started at 5,000. After one time unit, we dropped to 4,750. So clearly this is exponential decay. And so after 5 seconds, we should be even lower, which it appears that, yes, we are. So it does work out quite nicely. And that's how these rate of change proportional problems kind of work out. Anyway, I want you to look back at this boxed in thing right here as we move on to the definition of exponential growth and decay. So this is going to be quick because we've actually already seen this. This is the box that I told you to look out for back in example D. If we want to talk about exponential growth or decay, that growth or that decay is always going to be proportional to the amount that is left. Think about half-life here. How much will be left after so many years? Well, it depends on how much we had at first. And then, of course, how much we have after that depends on where we are. So that's exponential decay. As far as exponential growth, imagine keeping a bunch of bunnies in a cage. How many bunnies will I have a year from now in that cage, left to their own devices, of course? Well, doesn't that kind of depend on how many bunnies were in the cage to begin with? Alright, so that's how exponential growth and decay works. It does involve a lot of population logistics, but that's another lesson that we'll get to later. So if we go ahead and work this equation out, as we've already done before, we're going to start like this, And we know where to go with this. We've already done this, what, 4 times? So we continue on with that, integrate both of these, and end up with the natural log absolute value of y equals kt. And this is why that c is so important, because you can already foreshadow what's going to happen here. We're going to exponentiate both sides and end up with y equals c e to the kt power. Notice how important that c is. Alright, and that is our exponential growth and decay model, ce to the kt. How do I know when it's growth and how do I know when it's decay? All I really need to do is look at the value of k. I know that I'm going to experience exponential growth if k is greater than 1. And I know that I'm going to experience exponential decay if k is less than 1. And of course, if k equals 1, then I'll be at a steady state. And that's how all this looks. So with that, let's go ahead and take a look at a couple more examples involving half-life, because that's the greatest application of this. And here we go with example E. Alright, so here in example E, this is a half-life problem. This is dealing with the carbon isotope C14, carbon 14, which is very, very commonly used in radioactive dating. We know that carbon 14 does have a half-life of 5,730 years. You can look that up for yourself. It is scientifically accurate. Not exact, but accurate. And then we're given some information about some sample. 2 grams of it remains after 10,000 years. We'll get to that in a moment. But the most important thing is that we work out this half-life formula. So we know that this is an exponential decay. So we're going to use the y equals ce to the kt formula. In this particular case, because we're dealing with half-life, what would be the easiest, simplest amount of substance to start with? If you agree with me, you would say the easiest amount to start with would simply be 1 unit, 1 gram, 1 pound, 1 whatever it is. And if that's the case, then after this many years, we would have half of that left. So let me go ahead and start with that, saying we have 1/2 left of a 1 gram sample after 5,730 years. And of course it's k that I don't know that I need to solve for. So all I need to do is just go ahead and natural log both sides. No big deal. By doing that, what I'm going to get on the left is negative, let's see here, negative 0.693. And on the right, I will have 5,730k. Well, a little bit of math will get you where we're going here. We're trying to find the value of k, and let's see if I've done my math correctly. That value of k is about negative 0.000120. Of course, that is a constant. It doesn't have any units. It does tell us, because it's negative, that it is exponential decay, which is good. Half-life is exponential decay. And with that, we can go ahead and make our general solution to this half-life problem. And in fact, I'm going to argue that what that's going to look like is y equals ce to the kt. Alright, this is our general solution. We're going to use this to work out the next part of this problem, which says that after 10,000 years, we have 2 grams of this sample remaining. And they're asking us, well, how much was in the original sample? So let's work this out. Y is the amount remaining, so if we put 2 grams in for y, we'll get 2 equals ce to the negative kt. And t, of course, in this case, is 10,000 years. So I'm not going to go through and do all the math. You can do that for yourself. But if you do it correctly, what we should find out is that our original stock of this substance, whatever it is, was originally 6.704 grams. All right? And if you didn't get that as your answer, go back and double check your math. That is what we should get. And now knowing that, the last question is, how much of this remained after just 1,000 years? Of course, the original problem was almost 2 half-lives into the life cycle, which makes sense if we started with 6.7 and ended with 2. That is almost 2 half-lives. But here, we're dealing with less than 1/5 of a half-life. Let's see how this works out. Let me go ahead and start a new problem here. And what this will say is y equals 6.704 e to the k, and of course t this time around is just 1,000 years. Now we go ahead and work that out, and what we should find is that after 1,000 years, we are left with 5.940 grams. Well, that is less than we started with, which makes sense. This is decay. Are we at a half-life yet? This is certainly not half of what we started with. It's much more than that. And that makes sense because 1,000 years isn't even near a half-life. So that's how we use these half-life examples. I want to do one more example with you guys. This last example could be a little bit controversial. It does involve religious relics. Feel free to look up the Shroud of Turin before we begin the next example, just so you can get some historical and theological context to example F, and then join me as we find out the mysteries of the Shroud of Turin. Before beginning example F, I will state that the information in this problem is, for the most part, very accurate, but of course there are a lot of other conditions that are in play here, besides simply the mathematics and radioactive dating of the Shroud of Turin. Hopefully you've had a chance to research it. If so, you know that many theologians around the world consider the Shroud of Turin to be the burial cloth for Jesus, which would of course make it about 2,000 or so years old. Radioactive dating has been done on the Shroud of Turin a couple different times in the last 50 years or so. Most recently in 1988, when small pieces of the shroud, very small pieces, were sent out to labs in Tucson, Arizona, Oxford, England, and Zurich, Switzerland. All three labs came back with very similar results, the average of which was that the shroud contains about 92% of the carbon-14 that it originally began with. Now, if that's the case, if it still contains 92% of the carbon-14, the first question is, how old should the shroud be if that really were the case? The second question, if the shroud really were about 2,000 years old, which of course would give more credence to it being the burial cloth of Jesus, then how much carbon-14 should remain? Well, let's go ahead and take a look at this piece by piece. In the first question, we're given that 92% of the carbon-14 is remaining. If we want to consider the original amount of carbon-14 to simply be 1, we can consider that 100%, then what's left is 0.92. That's the 92%. Now, I'm not going to write the 1 here. It's really not necessary. And furthermore, it's not really that necessary for me to go back and find the value of k. It's a half-life, and with any half-life, k will be negative 0.693. So here is my equation. Of course, if I want to work this out, I do need to natural log both sides of this. If I do that, I'm going to get something like negative 0.083, and over here, of course, I'll just have negative 0.693t. From here, you can just divide and find out that according to these data, the Shroud of Turin is actually only about 690 years old. Clearly, that is not 2,000 years old, and so therein lies a problem with either the shroud itself, the belief behind the shroud, or the radioactive dating. Of course, many people will point to other things that have happened in the shroud's history, explaining as to why there is so much carbon-14 remaining. For example, it was in a fire some time ago. You can look it up and see for yourself. But while it was housed in the Turin Cathedral originally, it was involved in a fire there. So that might mess with the data. It's really not for me to say. I'm not a scientist. But the math certainly points at the shroud being this old. Now, if the shroud really were 2,000 years old, then how much carbon-14 would we expect to be remaining? For this, it's just a matter of plugging in for T. Of course, C, I don't really need here. I know that C is just going to be 1. That's the amount of carbon-14 that we started with. And then we'll have E to the K, which is negative 0.693, T, which in this case we'll call 2,000. Now, there's really nothing for me to show you here. I actually just ran this right through my calculator. And what I found out is that after 2,000 years, the Shroud should be containing about 79% of its carbon-14. But what we found is that there's actually 92% remaining, and so again, we run into that dilemma. Of course, I'm not sitting here trying to make any religious claims or go against any religious claims, but it is interesting to see how math is involved in history, archaeology, paleontology, and so on, and so on. And so, here in lesson 5.6, we continued what we had already started when we studied differential equations. We've been talking about differential equations every time a slope field has popped up. And now we kind of see how differential equations worked out. Here in this lesson, we worked with a certain class of differential equations in which the rate of change of a variable was actually proportional to the value of the variable itself. That's why we had a lot of y primes equaling some proportion of y. So from there, of course, we learned how to break that down and how that often, not always, but often resulted in exponential growth or decay. So we went ahead and looked at the formula that defines exponential growth and decay. I made a couple errors when explaining to you that the value of k tells us whether the function is growing or shrinking. I had said that k equals 1 is the cutoff point, but you read the corrections. You saw that if k is positive, then we're experiencing growth. If k is negative, we're experiencing decay. And if k is 0, we're constant. So we did look at that formula. We examined it quite a bit. And then from there, we looked at a couple examples involving half-life, which, as I said earlier, is the penultimate application of exponential growth and decay. So, very exciting lesson, lots of fun, interesting things, controversial things. We ran the gamut on this lesson. It's a lot of stuff, but hopefully the assignment will make sense to you. And so, as always, I wish you good luck.